I'll go grab it for you. How was the weekend? Pretty good. Good. There you go. What questions do you have? Is everyone all right? All right. Well, let's continue on. We talked about, pardon me, how to find orthogonal and orthonormal bases last time through the Graham-Schmidt process. I emailed you this morning solution. I finished off the solution of the problem that we didn't finish with the subset of 4 vectors in R5 and creating a orthogonal or orthonormal basis of that subspace generated by those 4 vectors. So that will be in your email. I know you want to probably grab a handout. Noah, you probably want to get a handout. Anyway, so sent that to you so you have an example. We also did an example, brief example of how you can do orthogonal bases, create orthogonal bases using in function spaces, and we'll see another example of a specific type of function space that we're interested in later on when we talk about Fourier series. So before we get there, we need to do a little bit of preliminary work to get to the idea of least squares. We'll do some examples of some least squares, curve fitting with, you remember to have a polynomial or a cubic function, one or the other. Also an exponential function, and then we'll also talk about doing Fourier series. So we'll give you some examples of why we care so much about this stuff, hopefully. All right. So before there, let's talk about what we refer to as an orthogonal complement. Before I write out the definitions here, here's the idea. If let's say we're in R3, just for argument's sake, and I have a subspace that looks like a plane. So a 2-dimensional subspace generating a plane in R3. Okay. Say this is my W. If I have a 2-dimensional subspace in R2, or excuse me, in R3, I've only got 1 dimension left, right? So, in the sense, right? So if I have a subspace that's not in W, then I'm probably going to have a subspace that's going to kind of complement R3. That subspace is going to have dimension 1. And when we refer to an orthogonal complement, orthogonal, again, in a Euclidean sense, makes us think of what? Perpendicular, right? So when we talk about orthogonal complement, what we're really talking about is the subspace that ends up being orthogonal to that plane or this line. So this would be in pictures W perp. Again, remember that the zero vector has to go through, the zero vector has to be in every subspace. So that line would be going through the origin. I just didn't draw the axes in there. Okay. So in the Euclidean sense, this is what we mean by orthogonal complement. If I have a subspace generated, the orthogonal complement is the piece that would be directly perpendicular to it and take up the rest of the dimensions. Okay. So, I'm not too worried about the dimension piece. I'm just more worried about the orthogonal complement piece here. All right. So going back to over what we have the definition here. If we have any subspace in an inner product space, the orthogonal complement, which we denote with this W with a little perpendicular sign, superscripted. The orthogonal complement of W is the set of all things in the vector space that are orthogonal to everything in W. Okay? That's what that means. So in other words, the orthogonal complement is the set of vectors in V that are orthogonal to every, and it's important that it's every vector in W. Okay. Yes. Say it again. The dimension idea is a consequence of this. I'm not too worried about the dimension part. If the dimension idea is just like we'll see it here in a second. why the dimension piece is what it is, but I'm not as worried about the dimension piece. But to understand why we only have this line over here in Euclidean versus something else, another idea you might think is, well, why couldn't it be a plane, right? Why couldn't I do a plane that's orthogonal, right? You certainly, if you've had Calc 3, have talked about the idea of perpendicular planes, right? Yeah, okay. But is every vector in the red plane that I just drew here perpendicular to every single vector in the other plane? No. Okay. For example, if I look at this line where they intersect, they're in both at the same time, right? They can't be perpendicular to themselves. Okay. So that perpendicular plane idea won't work. Because any vector that's in this line of intersection would have to be, if it's the orthogonal complement, would have to be perpendicular to itself, which it's not. Okay. So anyway, we'll talk, like I said, we'll mention a little bit with dimension. I'm not as worried about it. The idea is that it has to be orthogonal to every single vector in W. We use, I already mentioned that this is a little perpendicular sign that we use as a subscript, and we actually use that for a quick way to say the set. Instead of saying orthogonal complement, which is 7 syllables long, right? We say W perp. So we call it perp. Okay. So we would just say W perp for perpendicular, even though this can be in any arbitrary subspace, okay, or any arbitrary inner product space. All right, so let's show that this really is a subspace. To review, how do you show something in a subspace of vector space? What do you need to show? Closed under addition, closed under scalar multiplication, right? All right, so we also need to make sure it's not empty. What vector is definitely going to be orthogonal to every single vector by definition? 0 vector, right? Good. So since 0 is in W perp, we see that W perp is not the empty set. So let's let, we'll call them V and W perp. Oh, let's not call it W. Let's call them V and X, V and W perp. I'll use W for something in W. Okay. And we'll take a scalar in R. Okay. You already told me I need to show that it's closed under addition and closed under scalar multiplication. So I need to show that V plus X is back in W perp, and I need to show that C times V, say, is back in W perp, right? Since V and X are in W perp, what do we know? What's your defining characteristic for being in W perp? They're orthogonal to everything in W, right? And so that's our condition here, right? That when I take the dot product of any V with W, I'll get 0. If I take the dot product of X with W, I'll get 0, right? Okay. So then we know that V dot W is 0, which is the same thing as X dot W for all W and W. I want to show that V plus X is back in there again. So what do I need to show? Yeah, V plus X dot W is 0, right? Okay. Well, what do we know about the dot product with respect to vector sums? It distributes, good. And then what's each of those? Each of those dot products are 0, good. And again, this will be for all W in W, because it's true for all W and W for the X and the V. Hence, V plus X is back in W, perp. Likewise, I want to show that it's closed under scalar multiplication. So I need to show that C times V is back in W perp. So what I want to do with the C times V? Yeah, dot it with W, good. What can we do with the C? Yeah, take it outside the inner product, good. And then V dot W is 0. I got C times 0, which gives me 0. And again, this will be for all W and W. Hey, so funky looking W. Hence, your CV is back in W perp again. So we've showed that it's closed under addition. Show that try that again. Show that it's closed under scalar multiplication. Therefore, W perp is a subspace of V, not W. It's okay. All right. The next part is kind of the idea we talked about with the picture in R3. The only thing that is in W and orthogonal to everything in W is the 0 vector. Right? Now, certainly, one containment is true. Certainly, we have to have the 0 vectors in both of them, right? Because they're both subspaces, since W and W perp are subspaces of V. 0 must be in the intersection. That's certainly true. But to go the other way, we'll start with something in both at the same time. And we already mentioned this a little bit ago, but it's the same idea here. If something is in the intersection, then that means, of course, it's in both of them. If it's in W perp, what does that mean again? It's orthogonal to everything in W, right? Including itself, right? Okay? So since V is in W perp and V is in W, we must have that when I take that vector and dot it with itself, I get 0, right? The reason why is this is because we're in W perp. This is because we're in W. All right, if it's in both at the same time. What's the only vector that when you take the inner product with itself, you get 0? It's the only vector that does that. 0. Yeah, good. Which is what we showed. So 0 is in the intersection. If I take anything else in the intersection, it must be 0. So therefore, we must have the intersection just be the 0 vector. This is why we call them orthogonal. That's why we call them orthogonal complements. The orthogonal piece, of course, is we're creating all those vectors that are orthogonal. But the complement idea is that they really have no overlap except for 0. Okay? There really isn't anything that's in both at the same time besides the 0 vector. So they really do complement each other. You can also show that anything in your inner product space can be written as something in W plus something in W perp. They really do complement each other. Okay. Like I said, I'm not as worried about that. All right. What I do want to talk a little bit about is how do we find orthogonal complements? because this will be important with our idea with least squares. How do we find orthogonal complements? Well, it turns out that your null space of A and your row space of A, pardon me, are orthogonal complements in Rn. Let's see why. What was the null space again? Say again? Yeah, exactly. Yep, it's the solutions of AX equals 0. Exactly right. It's the space of solutions of the homogeneous system, right? Row space, again, was what? Oh, that's the dimension of the row space is number of pivots, right? But literally, what space is the row space? Yeah, the span of the row vectors. Good. That's all right. That's the span of the row vectors. Okay, right? So you're treating each row as a vector. It's the span of the rows, right? Okay. So let's think about why they're orthogonal complements, all right? Well, if I want to do A times X, let's say we have something that's in the null space, right? Well, let's think about how you multiply. How do I multiply A times X? Well, let me just do it off to the side. I'm not worried about what answer I get. How do these get multiplied? It means this row times that column, right? You would get AG plus BH plus CI, right? And the other one would be DG plus EH plus FI, right? What do these look like relative to what we've been talking about? What do those look like? Yeah, inner products, right? What are they inner the product with? What are they the inner products of? Well, that is the inner product of row 1 and that column, isn't it? This is the inner product of, this one is the inner product of the second row in that column, isn't it? Okay. So going back over here, if I think of my matrix A is just made up of these row vectors, and X is a column vector, then I really do get a vector that's, oops, the first component would be R1 dotted with X, the second two would be R2 dotted with X, all the way down to Rn dotted with X, right? Now, if I wanted that equal to 0, what would that say is true about R1 and X? If I want that equal to 0, what does that say about R1 and X? Or orthogonal, R2 and X, orthogonal, and all the way down, right? So if I'm talking about this X being a solution to my homogeneous system, then my X is going to be orthogonal to every single row. Well, if it's orthogonal to every single row, it's certainly going to be orthogonal to any linear combination of the rows, right? If it's orthogonal to every single one of these, it's certainly orthogonal to any linear combination because of our properties of the inner product, right? It'll distribute over the sum, and then you can pull all the constants out, right? You see it, or do I need to write it out? If I have C1R1 plus C2R2 CNRN, I lied. That's not RN. That's RM. There's M rows. Sorry. Luckily, changing an N to an M is pretty easy. Put another bump on it. Okay. Then again, we can distribute the inner product over the sum and pull all the constants out, right? So you'd have C1, R1 dotted with X, C2, R2 dotted with X, all the way out to Cm, Rm dotted with X, and you will get 0, right? So certainly anything in the null space is orthogonal to everything in the row space. And if something is orthogonal to everything in the row space, it's orthogonal to R1, R2, and Rm, and it'll be a solution to the homogeneous system. It works both ways. So they really are orthogonal complements to each other. This gives us some insight on how we can find the orthogonal complement. All right. In any event, they are orthogonal complements to each other. That's the big thing. Why is the next one true? If the null space of A and the row space of A are orthogonal complements, why do I know I get the orthogonal complement of the column space by doing the null space of A transpose? Sure. If I know that the null space of A and the row space of A are orthogonal complements, why do I know that the orthogonal complement of the column space will be the null space of the transpose? Yeah, a little bit like that. But why do I know that I'm flipping from column space to row space or vice versa? Yeah. If the rows become columns and the columns become rows, right? So let's think about it this way. We just said a second ago that the null space of A is the orthogonal complement. I'll write it with notations this way, right? You agree with that? So if I replace the null space, if I replace A with A transpose, I would have the row space of A transpose complement, right? That way. But what's the row space of A transpose? The same thing as the column space of A, right? Because they just get flip-flopped, don't they? So just using notationally what I have here, right? So my null space is the orthogonal complement of the row space. It doesn't matter what the matrix is. So if I start with the transpose, it's still true, right? This is a true statement for any matrix. I just replace A with A transpose, but now I know how rows and columns behave under transposes, right? Rows become columns, so I get the orthogonal complement of the column space of A. That's going to be important here in a minute, I promise. Okay. All right. Let's talk a little bit, though, about how we find a basis for the orthogonal complement. I want the orthogonal complement of the subspace of R4 spanned by those three vectors. Well, the thing that we know are orthogonal complements are null space and row space, right? Correct? Those are the things we just said are orthogonal complements to each other. So using that fact, how might you create a matrix to help you out? We know how to find null spaces using matrices, right? What do we do to find null? How do we find null space bases using matrices? What do we do? Like if you have a matrix already, how do you find a basis for the null space? Yeah, we row reduce, right? Right? We row reduce, don't we? And then we look for the free variables and all those things, right, for the null space. Okay. Once I have a matrix, I can do that, correct? Okay. how am I going to create a matrix here to do it? And that's what this is, why this is important. How am I going to create a matrix so that I can find a null space in this case? What do you think we should do? Good, exactly right. We want the vectors to be the rows in this case, right? And that's why I wanted to make a big deal out of it, which is why I'm having to think about it. Usually when we make a matrix from vectors, what do? We put them in as columns. You gotta be careful with orthogonal complements. They have to go in as rows because of this property. Okay? Okay, so they have to go in as rows. So we'll let our matrix A be 1, 4, 5, 2, 2, 1, 3, 0, negative 1, 3, 2, 2. Okay. It's pretty much the one time you're going to put these in as rows when you're finding orthogonal complement. Okay. All right, so now though, everything should be familiar. Get the reduced row echelon form. Yes. Because we're looking for the orthogonal complement of the rows of A. That's why we're putting it, because we're using the fact that the null space is the orthogonal complement of the row space. So I have to use them as rows in this case, because I need to create a row space rather than a column space. That's why. Okay. Anybody get the reduced row echelon form?
1, 0, 1, negative 2, or 2 sevens.
2 sevens, okay.
0, 1, 1, 4 sevens.
Okay. And then a row of zeros. Yeah, okay, good. All right. All right. Before I ask anything else, what's the dimension of your null space in this case? 2, because of why? Why is it 2?
That's the two ones that are not.
Good. Two pivotless columns here, right? Remember, dimension of your null space is number of free variables. So there's 2 pivotless columns. That dimension is 2. What's the dimension of your row space?
You said what?
What's the dimension of the row space?
2.
Because there's 2 pivots, right? Yeah. Okay. So there's 2 pivots, that's the row space. There's 2 pivotless columns, that's the null space, right? Notice in this case, they really do match up, right? Remember that rank nullity theorem? Remember that thing? The rank plus the nullity is number of columns. That's really what tells you that you really do have complements here and their dimensions add up to what they need to. Okay. All right. So let's look at for your basis of your null space. Your free variables would be those two, right? So if you had an x1, an x2, an x3, and an x4, I've got one free variable where the x3 goes, and I've got one free variable where the x4 goes, right? Looking at this first row, you would have a negative s. Oops. Maybe should have made this a little bit bigger. I'd have a negative s and a positive 2 sevenths on my t. And the other one would have a negative s and a negative 4 sevenths on my t. I got to move them to the other side, remember? This is my S column, this is my T column, but I have to move things to the other side, which is why they flip-flop. Right? All right. So it's asking, this would be your set of solutions. It's asking for a basis, so your basis would just be those 2 vectors. I'll write them as rows. I don't have to write them as rows. It doesn't really matter. Notice, though, you're not doing anything new, right? We've done this before, haven't we? Nothing about this process after we created the matrix is new. We've done this. Since the beginning of the semester, we've done this, right? This literally isn't new. The only thing that is new and a little strange, because it goes against everything else that we've done so far this semester, is making that matrix from using the vectors as rows rather than columns. That's the one little strange piece, right? But once you've got your matrix created, everything else is done just like we did all semester. It's kind of nice. It's nothing new, right? I think it's kind of nice when it's not new, right? Tying everything back to what we did earlier in the semester. Questions on this example? Yes. Why don't we use what? I'm sorry. We're finding that remember we're doing the orthogonal complement of the row space. I need to find the null space. That's why I'm working with the null space. Is that the problem's not asking for a basis for the row space, it's asking for the orthogonal complement. It's asking for a basis for your null space. That's why. Okay. That's it, yeah. That's it. That's the whole problem, yeah. That was it. Make your matrices rows, row reduce, write your solutions, and figure out what your basis is. Yeah. I know, it seems kind of anticlimactic with all the work we did into it, right? All right. Let's go back to mega theorem. We got a couple more conditions that we can put on here. I don't even know what letter we're on at this point. Number 19. What is that, S? Whatever letter that is, number 19 is S. Okay. All right. So we're going to have 3 more to add. I told you we were going to get to 20. The orthogonal complement of the row space is 0. The orthogonal complement, and we're not even done yet this semester. The orthogonal complement of the null space of A is all of Rn. Those are the 2 that we have added in today. Okay. Why do we care? A lot of work for something that didn't seem very difficult to find relative to what we've already done this semester, right? So why do we care about orthogonal complements? Well, they have to do with orthogonal projections, and orthogonal projections have to do with least squares analysis. Okay, this is why we care. Right. So let's talk about how we find an orthogonal projection to something. So you're get a black and white copy. Hopefully this is a little bit better. All right. So to explain what's going on with the picture, my light blue shaded here, which is probably gray on your, or lighter gray on your papers. This is representing a subspace. So I've got it labeled as a W in there, representing a subspace. Okay. It's in R3, so it's 2-dimensional here. Okay. But generally speaking, this is the same setup as what we would have. What I want to try to figure out is this greenish vector here. Basically, it's a shadow of my U sticking up, right? So I've got some vector U not in my subspace, and I want to project it onto the subspace. Okay? Now, we could do that using techniques that we did in the last section. Remember, if we have an orthogonal basis, we can do projection just by doing dot products, right? We talked about that in the last section, okay? Try to have a little bit more general method to do this so we don't have to go through and have to find an orthogonal basis every single time, okay? All right, but anyway, this is the projection. So the orthogonal projection straight down would be that perpendicular line from that point going straight through W, right? Basically, it's the orthogonal complement just shifted to the tip, right? So if I found the orthogonal complement here, I could shift it over to the tip and I would find the projection just by doing that intersection. Okay? Basically like a shadow, if you will, on the subspace. All right. How do we do that? Well, let's think about it this way. If I, pardon me, goodness gracious, if I could solve, just thinking generally here, if I thought about trying to solve that particular system, this would mean that my u, so if x is a solution, then my u is actually in the column space of A, right? If I can find that solution, right? We agree with that? If I can find that solution, then my u really is in my column space of A. Okay. All right. Goodness gracious, sorry. All right. Now, the way I have this drawn is u. Am I going to be able to solve this system the way I have it drawn? No. Right? I purposely picked a vector that wasn't in there, right? In some sense, I want to find the vector in my subspace that best approximates that vector, being the shadow, right? Okay. I want the vector that best approximates this view, the u here, but being in my subspace. And then now maybe you can start to see the idea of the least squares coming up, right? I want to try to approximate something that's not a solution, right? Okay. So let's think about how we might do that and why we might want this particular vector here, okay? So, and this is where the idea of least squares comes from and where we're going to get to this point here, okay? So, if, pardon me, if W is a subspace and W is in, little w is any vector in W that is not the projection of U onto W, the subspace, then the magnitude of U minus W will be less than the magnitude of U minus, greater than, not less than, greater than the magnitude of U minus the projection of U onto W. And it kind of makes sense when you think about the picture. I'm trying to figure out what's the shortest way to get from this tip down to my subspace, essentially, right? Because that would be the length of this, right? We agree? Okay. So it makes sense why that has to be true, because if I try to go any other direction, that's going to be longer than just going straight down, isn't it? We should probably prove it, though, because this is all thinking about it from a Euclidean geometry standpoint versus an arbitrary inner product space. All right, so how does the proof of this go? Well, rather than worried about the magnitude, I'm going to worry about the magnitude squared. Okay. We're going to cleverly rewrite 0 because we're clever like that. I'm going to add and subtract the same vector inside. Let's think about why I did that. Let's ignore the first half. Where does little w live? In W. Where does the projection of U onto the subspace W live? in W because we're projecting it into the subspace, right? And if I add or subtract two vectors in W, where does that end up? In W, because it's the subspace, right? Cool. All right, so this part is in W. Okay. What about this part? Well, if I projected this onto my subspace and then I subtract my U, that's orthogonal to everything in W. Right? It's going to be orthogonal to everything in W. This will be in your W perp. Yeah. Yep. W perp. Yep. Okay. All right. So now I have two vectors that are orthogonal with a plus sign in the middle. Good news is that in any inner product space, the analog of the Pythagorean theorem holds. And you can prove it. If X and Y are orthogonal, then they split up. Basically, it looks like it splits up. It's a result of the Pythagorean theorem. Okay. Think about why it's a Pythagorean theorem. If X and Y are orthogonal, then X plus Y goes between them like this, doesn't it? It looks like a Pythagorean theorem, doesn't it? That's not a hard thing to prove, by the way, because how do we rewrite magnitude squared? What's our definition of magnitude squared? It's equal to the inner product with itself. Just do the inner product of X plus Y with itself and multiply it out. The things in the middle will cancel. You'll get X dot X and a Y dot Y when you're done. All right. So anyway, why do I care? I can split this into pieces. Right? That's the Pythagorean theorem I just mentioned, right? They're orthogonal to each other, so I can split it into two pieces. Okay? Notice I said that if I have a vector that's not the projection, is this going to be the zero vector then? No. And if it's not the zero vector, can this thing be zero? No. So I'm really, honest to goodness, adding something, aren't I? This really is greater than the first term. And now take the square root of both sides. Okay. This is why we say least squares, by the way. When I'm finding this projection, it gives me the least possible square of the magnitude. This is where the word least squares comes from. Okay? I'm trying to make this as small as possible. What makes this as small as possible? That projection. So this really is, what we're saying by this is that this projection really is the best approximation of this vector that lands in the subspace. That's the idea. Okay? All right, so let's go back to how do we find it. Okay? I started that off and then I went off on what seemed like a tangent. Okay? All right. Go back over here again. I'm trying to solve that system. That's hard. Probably impossible, right? Okay? So instead, we solve AX equals the projection of U onto W. Now, again, that seems a little strange because I'm actually trying to find the projection, right? But we'll get there. We're going to be clever. We like being clever. We're mathematicians. We like being clever. Okay? All right. Now, again, remember, if I have a solution, it's in the column space, right? Okay. What did we say was the orthogonal complement to the column space? Yeah, the null space of A transpose, right? So that's going to come here in a minute. All right. But to get to that idea, to get to a null space, I need the 0 vector, right? To start with. Okay. So let's do the following. Let's do u minus ax and u minus the projection of u onto w. Now remember again, I'm thinking about column space here. Let me think about, this is my w. Okay. That's my w. Where would this live again? W perp, right? Because it's perpendicular, it's orthogonal to everything, right? The orthogonal complement of the column space is the null space of A transpose, right? So let's multiply both sides by A transpose. The reason why we did that is why. This is in the null space of A transpose, so this has to be 0, right? Now we've got a nice little equation to solve. That doesn't involve the projection at all, does it? Now we've got, if I rearrange my equation, we have A transpose A times X equals A transpose U. I'm not going to prove it. But this always has solutions. No matter what, this is always consistent. Notice also that it's a square system. A transpose A will be square, won't it? All right. What would be nice to be able to do to both sides to get rid of this? It'd be nice to have an inverse and go over to this side, wouldn't it? This will always be invertible. We can prove this too, but I'm not going to take the time. If A has n linearly independent columns. Okay. You can always do the inverse. But if you have linearly independent columns with your A to start with. Okay. So then your solution will be A transpose A inverse times A transpose times U. That's going to be the solution. I'll do the inverse to the other side. Okay. And then finally, to get to the answer we wanted, your projection onto W will be A times this X. I'm not going to rewrite it. That goes in for X. Okay. So we get at it a little backhandedly. So let's see if we can actually do this problem. Okay. The first step in the problem is to make a matrix that is the column space that you're interested in. So that's usual, right? We're going to take our matrix, we're going to take our vectors, make our matrix A. Okay. At this point, we're just going to follow the formula. Okay. First thing I need to do is take A transpose times A. What size matrix are you going to get if you do A transpose times A? Two by 3 for the transpose, 3 by 2 for the original, so you're going to get a. If you do a 2 by 3 times a 3 by 2, you get a 2 by 2, right? Yeah, we should get a 2 by 2. Because you'll have 1, 1, 0, 1, 2, 1 times the other one. Right? What do we get? 2, and then 3, and this better be 3, and then we get what, 6? By the way, A transpose A, we did this earlier in the semester. A transpose A is symmetric, right? I better get a symmetric matrix when I'm done. Right? Okay. So now you do A transpose A inverse. That's the next step, right? Looking at my formula over here. Right? How do we do the inverse of a 2 by 2? Yeah, the AD minus BC, 18 minus 9 will give me 1/9. And then you flip the main diagonal and negate the off diagonal. Right? Yeah. And then we take this times my A transpose. Right? So what's this do here? It's the next thing in the line, isn't it? This is why it's going to be very important to have your calculators on these, right? Do you have a question?
Is it 12 minus 9?
Yeah, it should be just 12 minus.
Oh, it's 12 minus 9. Well, that's much better. Thanks. I don't know why I did. Well, 6s and 3s are flying around. Thank you. Okay. See, you played. Okay. Anyway, you finish that off. You multiply it by the u. I know we're out of time. Multiply it by the u. That gives you your x. That gives you the solution to the system, right? If you actually want the projection, you take your original A times your solution, and that'll give you your projection. I'll finish it up and email it out to you so you can see the solution a little bit, so you can actually read through it. We're going to use this for the least squares solutions, by the way. So this particular formula right here will be what we're going to use to find least squares solutions next time, okay? And then we'll get into Fourier series as well. All right. Have a good one. We'll see you on Wednesday.